Dihedral groups are defined as follows. For n bigger or equal to 3, we define Dn to be the group generated by two elements, G and H, with the following properties. G to the n is E, so G is of order n, H is of order 2, and they have one more condition among them, one relation that is H times G times H inverse is G inverse. Out of these properties, you can prove that Dn has exactly 2n elements, and you can write every element in this form. It's E, the identity, the powers of G, and H times the powers of G. And any element, any combination of letters, any word in G and H can be reduced to one of these 2n elements. These are natural and useful groups to study because they correspond to the rigid motions of a regular n-gon, a regular polygon with n sides. So they correspond to the symmetry groups of regular n-gons. So for example, here I've drawn the rigid motions of a equilateral triangle, and there are 6 such motions given by the identity, the one that does nothing, a rotation of 120 degrees, a rotation of 240 degrees, a reflection along that line, and then another 2 reflections. And then you can see that you can actually write them all in terms of G and H. So for example, this one is H times G. One of the interesting properties of these groups is that these are some of the first examples of non-abelian groups, non-commutative groups, because these motions do not commute with each other. It matters in which order we do them. So for example, here I've done a rotation first and then a reflection along that axis, and I get this motion, the motion that from here to here fixes 1 and flips 2 and 3. But if I do H first, if I do the reflection first and then the rotation, then I get a different motion, because now it is 2 that got fixed and 1 and 3 got flipped. So what that means is that H times G is not equal to G times H. In fact, G times H is H times G squared in the notation we had set up at the beginning of H times powers of G. And that comes down from the initial property that we had defined in the group, that H times G times H inverse, but H and H inverse are the same element, is equal to G inverse. So you can show that G times H is H times H squared times GH, because H squared is identity, and then distribute elements to show that that is H times G squared.